In this section, let's take a look at some compression utilities that are common across Unix-based systems, FreeBSD included. So we'll log in as the user, Unix CBT. Then bring up an instance of gedit from our command history from a bash shell. Any program that we bring up on the desktop can be found, usually, if it's GUI based, somewhere in the applications menu or in one of the above menus. However, if you know the name of the binary, you can call it from the command line, which saves time. So accessing our command history using !gedit, what this does is it pulls up the most recent invocation of gedit, which is instance number 85. So !85 saves us time. This will bring up our notes momentarily. So we like to cover compression utilities because they're often used. And even in today's bandwidth replete environment, it still makes sense and is advantageous to move data across the internet, across the globe, in a compressed form, perhaps attached to emails, which is ill-advised, as email wasn't designed to carry large attachments, but they're used invariably to do so, or simply using traditional transfer protocols such as FTP, or more modern incarnations such as SFTP. So we'll label this section Compression Utilities. And as the name implies, the features include, the primary feature includes reduction in footprint of data set. Now currently we have no data set, so we'll have to create our fictitious sample data set in order to illustrate the tools that are available to us. There are a number of compression tools. Perhaps the most commonly used are gzip, bzip version 2, and zip. Zip ensures compatibility across platforms such as Windows and Unix. gzip and bzip version 2 ensures that you'll be able to be compatible with Unix-based platforms and optionally with Windows-based platforms if the appropriate tools are available to handle the file type. So, some tasks include: 1, we need a data set. So create data set. Now we like to work with a small file, something such as 10 megabytes, where we can readily see the improvements or gains from compression. So one simple way to create a 10 megabyte data set is to use the DD utility. Another is if you have a sequence generator such as seek, which is included on virtually all Linux distributions but is not included with FreeBSD by default. So we'll use DD instead, as it's included across all Unix-based distributions, Linux and Unix. So DD, and it supports a number of options, but the key ones for us is we need to instruct DD where to get its input from. Now, Unix-based systems provide a variety of input sources. One common one for generating sample data is dev0. So we'll set an input file to dev0. This tells DD to read its input from dev0. We'll set an output file of 10 million or 10 meg, doesn't matter, 10 million, since its size will be 10 million bytes, or 10 megabytes, which is slightly more, 10 million dot text. So it'll be approximately 10 megabytes, or it will be 10 megabytes, approximately 10 million bytes. Larger, however. Now, we should specify the byte size. What this tells DD is, as it fetches data from dev0, it should write to the file, read and write to the file in chunks of 1024 instead of its default chunk of 512 bytes. So it'll pull in globs of 1024 blocks on the input and output sides. So byte size equals 1024. With a byte size of 1024, this makes our multiplier much easier to amount to 10 megabytes, and that's where we set the count. The count allows us to tell DD how many times it is to iterate through this particular routine, which is to pull in from dev0 in blocks of 1024 bytes. So the count will be 1024-0, or 10,000 times, 10,240 times 1024, which will get us our 10 megabyte file. So this creates a 10 megabyte file for us to sample. So again, DD will iterate through dev0, pulling in blocks of 1024 bytes, and it'll do so 10,240 times. So let's pull this window over a bit, and we'll open a separate shell, which will give us a new TTY. Let's do a which DD. It's available to all users. It's included with the standard NIX base system because it's in /bin, which includes all of the key binaries that are to be included with a standard NIX system, which means it's a required binary. So let's go ahead and paste that in, and we'll have this file generated momentarily. So rather quickly, we see that 10 megs were transferred. Now let's do an LS/LH of 10 million.txt. And as you can see, it's 10 megabytes. Let's do a file against it to see what type of file it comes back as. It's simply a binary file, a data file. So now we have our 10 meg file. So we have our footprint. So on to compression utilities. One is gzip. Perhaps most commonly sought on the internet or noticed on the internet is the extension .gz. BZ2 is also popular, but gz is definitely more available online in terms of the way files are distributed because of compatibility. For example, gzip is read by Windows-based tools such as WinZip. So to create a compressed form of this, let's use gzip to compress data. We'll execute gzip with the create option, and that's simply C. Now we include the input file, which is 10 million.txt, and we use output redirection or clobber redirection to create the target file, which we'll simply call 10 million.txt.gz. So this is a simple redirection. So gzip will read on its input stream 10 million.txt. It'll apply the compression routine and send the output to standard out by default, but because of our redirection, the output will be sent to a file named 10 million.txt.gz, which will be compressed. Gzip supports a number of formats or a number of options, which includes how the target file will be formatted in terms of compression. So you can alter the compression strength as one example. So let's take this block, and gzip help will tell you about those additional options. Now let's echo the exit status. Nothing fancy happened, but the status is 0. That tells us the file was created. Let's LS/LH 10 million star, since there are now 2 items. So look at the major differential from the source file 10 megs to 10K. Insofar as transmissions across broadband networks, this is a major difference. Orders of magnitude, 10K, 100K, 1 order, a meg, 2 orders, 10 megs, 3 orders. So 3 orders of magnitude differential in the compressed file. We've been able to reduce considerably the footprint of the file, and this is certainly more desirable to attach to emails, so long as, of course, the target user has an appropriate decompression program that supports gzip compression. And so far as gzip's extra options are concerned, just run the help option. You'll see, for example, options including the ability to set the compression level to stronger or weaker, with 9 being the best compression but slowest, for example, and some other options, whether to recurse into directories, to list the contents of the compressed file, and so on. But the key is that's how you compress a file. Now, if you'd like to learn more information about a compressed file, since now if we do a file against 10 million star, you'll see that one's a data file, the other's a gzip compressed data file, and it knows that it was a file named 10 million.txt from a Unix-based system with a timestamp associated with it. So if you'd like to learn more, use gzip with the L option against the gzip compressed file. And this tells you a lot of useful information, including the fact that it was compressed to 10K, uncompressed, it's 3 orders of magnitude larger, and it was almost 100% compression. Amazing. So let's include this additional option. That's gzipl against the name of the file. Text gz enumerates compression stats using the L option. Now to decompress this item, you can use gunzip or gzip with the D option, which gunzip calls. So let's decompress this file. In fact, we can remove the original file to save on space. So let's remove 10 million.txt, which leaves us still with 10 million text gz, saving us considerable space. So let's decompress this item using gunzip. And this decompresses the item to its original glory. And let's echo the exit status. And there we see the original file. Let's clear screen LSL 10 million. And there's the original file. When you decompress, it removes the compressed version of the file, which makes sense. So decompresses the file and removes compressed version, which means in order to recompress this, in fact, let's do a file against 10 million.txt just to be sure that it's been restored. And as you can see, it's 10 million bytes. So let's history grep gzip and rerun 152. Now, by the way, the suffix .gz is unimportant, and that's not 152. We want 147. So the suffix is unimportant. Once you've compressed the file, it will be of type, encoded of type gzip. So let's do a file against 10 million text gz. And now we see that it's there. However, also keep in mind that when you do compress, unlike gunzipping or decompressing, the source file is retained. So let's just note, compresses and preserves source file. So we end up with both copies. And this gives us an opportunity to ensure that things have worked well before we move on to removing it. So transmissions becomes much, much easier with this reduced footprint. But gzip is only one format of compression, so we'll be looking at bzip2 momentarily. But let's just illustrate one other point. So let's move 10 million.text.gz to simply 10 million.text dot unknown dot compression, for example. So now we have two files with the prefix 10 million.text. The second, which is 10k, claims its suffix is unknown, but a file against it will still reveal that it's a gzip compressed file. And we are still able to decompress from the file. So let's remove the source file 10 million.text, echoing the exit status. And then let's recompress it, or gunzip it, which should be somewhere close in our history. So gunzip 10 million.text dot unknown compression. This will reconstruct the original file. Now, insofar as options that you can pass into gunzip, run it with help, and you'll see those options. For example, you can dump the standard out. You may be wondering, why would you ever need to do this? Well, most of the log files created by FreeBSD are written as simply text files. And there may be times where you'd like to gunzip on the fly and dump the standard out as opposed to a file. So the standard out option can be quite useful if the source file, the compressed file, results in textual output. So there are opportunities where you need to dump the standard out, or it's helpful to dump to standard out. So let's gunzip. We'll do a history grep. And we'll take in option 155. However, the file name is slightly different, so let's gunzip 10 million text unknown compression. Now notice, let's echo the exit status. It comes back as 1. Gunzip is programmed to look for .gz suffixes. So it doesn't recognize this particular suffix. It's not sure what to do with it. In fact, it's being driven or bases its entire decision tree on the suffix .gz. That's why this suffix option exists. So you can influence a different suffix to drive gunzip by using the S option. So in this case, it simply ignored it, doesn't recognize it. However, if you use the S option with a suffix of unknown, let's see if it'll take the 2, unknown compression, and this time it doesn't throw an error. And the exit status is still what we expect. So now we have the original source file. So let's copy this string into our notes. Some programs will only take one suffix, but in this case, it took everything verbatim. So decompresses with specified suffix. And again, that's simply because gunzip is programmed to look for a file with a suffix of .gz. Now let's just create one more gzip version of this file so that we can compare with bzip version 2. So history grep gzip, and we'll use the example 162, and this will create the traditional .gz suffix. Now an LSLH of 10 million star reveals 10 megs, 10K. So both are back in place. Now another program that may be of interest, in particular for gzip compressed log files, is zcat, which we like to point out because oftentimes log files are compressed using gzip compression. So zcat followed by file, G unzips the content on the fly and dumps to stdout, standard out. Standard out, as we've mentioned, is our default file descriptor numero uno, or number 1. So as we've mentioned earlier, in the dev tree you've got beneath the fd directory 3 file descriptors which are standard across NIX-based systems. So 0, of course, as we've mentioned, is input, 1 output, standard out, and 2 standard error. Oftentimes you'll see in scripts standard error routed to standard out, or 2 sent to 1. Also notice that these file types have a leading bit that's not a D nor a hyphen, but rather a C. Those indicate that they're character devices, as opposed to directories or files or name pipes or other types. So these are character devices. And oftentimes characters are supplied by the keyboard, but there are other means of supplying characters, such as on standard in via various files. So again, 10 million text star, these are our files. Now zcat, against the compressed file, will dump to standard out the contents of the file. But this file is a binary file, so it'll corrupt the screen in many cases. So it doesn't help us in this case unless the data happens to be textual. Zcat's the utility that's useful. And notice that the options are identical to gunzip, gzip, because really it's just a special invocation of gzip. So it decompresses on the fly, but the data happens not to be textual, so it doesn't display. You could zcat to a file, for example, which would create the file on the fly using output redirection. So, for example, a zcat of 10 million text gz to, let's say, 10 million text dot, let's say, zcat, for example, echo the exit status. Now let's LSL trh or tr. We can read the bytes. 10 million text, and that shows a version of the file with a .zcat suffix, but it's still a binary file. So 10 million text zcat shows that it's binary. It's a data file, so we're not able to interact with it on any intelligent level. So we can try to dump it, and that's what's inside the file because we use dev0 as a source. So let's clean this one up, and we'll remove 10 million text zcat, and we're back to just our 2 files. So that's enough time on gzip. Perhaps it's sensible that we spend so much time on it because it is the predominant compression form on the net. Now, the other forms, bzip version 2. I prefer bzip version 2. As I've often mentioned, it provides usually superior performance and savings in size or a reduced footprint. So Sometimes it's slower, so let's not say it's always better performance-wise, but ultimately it usually ends up resulting in a smaller footprint, which is why I prefer it. But then the caveat is not every recipient will have a BZIP version 2 capable client, especially Windows clients. However, if the target has, let's say, WinRAR or a similar program, they should be able to interact with BZIP version 2 files. So let's look at BZIP version 2. So the syntax is very similar to gzip. To create a BZIP version 2 file, you simply reference bzip2 with the create option, the source file, 10million.txt, which is 10 megabytes, and then the target file using output redirection. Let's say 10million.txt.bz2. So again, oftentimes on the internet, you'll see files that are available as .bz2 or .gz, and usually prefixed with .tar to indicate that there's an archive contained within the compressed file. So create bzip2 compressed file. So if you pull source code or programs from the net using bzip2 or bz2 as a suffix, then you'll need to take a look at using bzip2 to unzip or to decompress that particular item. So let's take a look at what we've got here. We'll create our new file, and just like that, it's been created. Now let's compare and contrast. And both of these programs, by the way, support a verbose option, so you can see what's happening during the process. But as you can see in both cases, it's so quick, it's so rapid that perhaps it's a moot point to run it. Now let's look at all of our 10million.txt files. So as we can see in this particular case, the bzip2 formatted file is still orders of magnitude smaller than even the .gz version. This occupies 49 bytes. So this tells us that the bzip2 algorithm is much more efficient than the gzip algorithm, which is good enough for us. Either happens to be good enough for us, but if you think about broadband constraints, which includes limited bandwidth and numbers of people sharing those constraints, then 49 bytes is always going to be easier to transmit than 10,000 bytes. 10,000 bytes in today's connected net is no big deal, even over dial-up, but 49 bytes is even smaller. So in this case, it's 49 bytes. Now, in terms of orders of magnitude, which happens to be 10, so from 10K, one order of magnitude smaller would be 1K, one order of magnitude smaller would be 100 bytes. So we've got 2+ orders of magnitude smaller between gzip and bzip version 2. So 49 bytes. Big difference. And just like with gzip, we can unzip and we can interact with the file. In fact, let's bzip to help, and you'll see the options that are available. So you can decompress with the D option. You can run bunzip2, for example. You can turn on verbose mode, which will enumerate information on the fly, etc. So to decompress this file, simply bunzip 2, and the default, of course, will be to send the output. So let's go ahead and decompress it. bunzip 2, 10 million text, bzip 2, and this knows that the file already exists. So let's look at the entire set. So the default for this particular program is to send it to the original file. For gzip, it's to send it to standard out. So there we see the original file exists. So 49 bytes, 10,000 bytes for the gzip formatted file. Now, just as is the case with gzip, bzip version 2 has a program, a counterpart program to zcat called bzcat. bzcat on the fly will display the content without decompressing the file. Again, this is helpful for log files where you need to look at content. We can take a copy of a log file, for example. So let's do that. So let's just note bunzip2 and the name of the file. So 10million.txt.bz2 decompresses to original file name. And the counterpart to zcat is bzcat file, which decompresses on the fly. which can be quite useful. Now, insofar as log files are concerned, since we're often dealing with textual data within NIX-based systems, let's just define as an ancillary task compress, and we have to be careful how we use the word compress because there is a separate program with its own algorithms called compress, but by compress we simply mean to shrink, to reduce. So compress active log file using both technologies. And we'll also include zip momentarily. So we need a file, var log. Let's take a look at the xorg log file. We'll just take a copy of it. So var log, and we'll have to take, of course, a log file that we have access to. So as the user Unix CBT, we appear to have access to messages, and it's 44,577. Let's look for something bigger. This is 103,959, but perhaps messages. Let's take a look. Let's head the first 5 lines from var log messages. This looks good. It includes all the timestamps, so this is perhaps a better file. So we'll use the var log messages file, the generic system log file, which is available across all NIX-based systems. So this is our file, var log messages, and we'll run. Let's use command chaining with logical ending to generate all of the various files. So we'll string together one long command, which gives us a little practice. So we know that we'd like to have, at least for the moment, a gzip as well as bzip version 2 compressed version of var log messages. Now we need not copy the file before operating on it. We can operate on it in place, active, and just send the output somewhere else. So we know the source is var log messages. So let's start with gzip. So gzip create, we want to create from var log messages messages.gz. Now if that's successful, we'll use $& to include or to indicate logical ending. If that's successful, we'll then bzip version 2 create out of the same file var log messages, sending it into a file named messages.bz2. So this is logical ending. In order for bzip2 to execute, gzip has to execute correctly, meaning returning or rendering an exit status of 0. We've mentioned that both programs support the verbose option, so since we haven't used it, let's enable it for both of these. And then we'll take this long string and execute it from the shell. Both will rely on the same source file. However, just as an FYI, since we're using an active var log messages file, there could be a slight discrepancy if log entries come in between the time that gzip executes and creates the output file and bzip2 executes. So there could be a slight discrepancy, maybe a few records. Depends on how busy the system happens to be. In either case, you'll take snapshots. So the initial invocation will take a snapshot using gzip, subsequent using bzip version 2. So let's see what happens. So here's the first incarnation, and let's take a look to see what we've got with respect to messages. And there are the 2 files. Now notice that they're both very close, although bzip version 2 still edges gzip out. But they're very close. They're negligible. Both are now ready to be transmitted across the net using any protocol. Now let's take a look at the source file. Now we don't need to look at what could have changed. We could use gzip with the L option against messages gz, and we'll see the original source file. So the compression ratio was roughly 86%. Uncompressed, the file expands to 44,577, and compressed it's 6K, just about 6K, 5.9K. So this is the differential. In terms of order of magnitude, it would have to be times 10. So from 6 would be 60. So it's somewhere just under an order of magnitude gain, which makes it much easier to transmit. Even the original file would have been okay. And same thing for bzip version 2. It's roughly within an order of magnitude, not quite an order of magnitude. So we've now created 2 files of that type using gzip as well as bzip version 2. Now, let's show you an alternate way to run this command. Using the bash shell, we can use variables to reduce our strings. For example, instead of executing this full string as follows, re-entering the source file name, we can define the source file as a variable. So for example, we can call it, let's say, L file. And we can export it on the fly. L file equals var log messages. And then simply reference this variable L file. Export's one way to do it. We don't have to export, we could just set it either way. So now instead of referencing that, we reference L file, and that reduces the string. Now, if there's something else that's in common, such as the prefix, then that we could also reduce so that we don't have to type in messages twice. But this just simplifies things a little, so you get the picture. So let's try this. This will overwrite the existing files. And let's re-LSL from our history, messages star. So there are the new invocations of the file compared to, so a 3-minute differential on both files. So you can write variables to reference the files and then just plug the variables in wherever you call them, so that you don't have to retype the same thing. Varying only what needs to be varied, which in this case includes the suffixes depending on the compression type that's in use. So now insofar as bzcat is concerned and zcat, well, let's first zcat messages gz. And there you see the contents. And of course we can pipe it into a pager such as less. And then we can navigate through it to see if there are any problems insofar as the kernel and other items are concerned. Like for example, here's some negative messages concerning pulse audio. Well, this BSD box doesn't have an audio card, so this module is failing to load because there is no audio support. bzcat against messages bz2 does the same thing. So you can confirm this with simply zcat messages bz2 and bzcat messages, and this is zcat messages.gz, and this is bzcat messages.bz2. Dumps output to stdout. So we've covered so far bzip2 as well as gzip. There's also zip. Zip's important because again it's ubiquitous. So 5 zip. Now the format of zip is slightly different in terms of creating the output file. We rearrange things slightly. So instead of specifying the source file then destination, it's destination then source file. So using the same examples, in this case we'll use the messages file. So instead of saying zip messages .zip, which is the target file, or the source file, messages, varlog messages, so we have it as a variable called L file. So instead of saying zip L file, output redirection, messages.zip, which is the format used with bzip2 and gzip, we change this around. It's simply zip target followed by the source file, which we have stored in a variable called L file. So creates messages.zip file based on L file. Well, what is L file? Echo L file. It's a variable that's set. It's currently defined in our environment because we have exported it. So when we print environment and then grep, for example, LF, we see L file is defined as varlog messages. That begs the question, is L file defined across shells? This is sudo terminal 1. So Control-Shift-T, let's print env grep LF. It's not available. When a new shell is launched, it reads by default the bash file for profile or bash rc if it exists in the home directory. At the minimum, it reads the profile file from etc. In order for variables to be available across shells, you need to export the particular variable via a startup file such as bashrc or bash_profile. Those are both hidden files. So this export pertains only to this particular TTY, which is pseudo-terminal number 1, or the second pseudo-terminal. So L file still exists. So let's just go ahead and use this. This saves us from having to type in the full name, and it'll be messages.zip. So now we can see it's achieved 86% compression. Let's LSL messages star just to compare and contrast. So messages.zip is the largest of the three which we expected. gzip outperforms zip, bzip2 outperforms gzip. And then we can zip L just as we can with bzip2 and gzip, messages.zip. And let's take a quick look. That's unzip L. Messages.zip, and it shows us the contents, its original size, which it represents as a column named length, and what it recreates. Zip also maintains the full path hierarchy. So the source file, let's echo L file again. It's actually up top, but we'll just echo it again. The source file was referenced from a full path of /var, absolute path of /var log messages. So that path was preserved in the file name, which begs the question, if we unzip it, what will happen? So let's go ahead and unzip it. To unzip, we use unzip, just like gunzip and bunzip2, that is. So unzip L file enumerates stats. Compression stats. Unzip file, which in this case is messages.zip, unarchives the file. So let's go ahead and do that. It's going to be messages.zip. So what is that recreated for us? Let's lsltr. Notice a new entry which is 512 bytes. var, and beneath var is a directory named log, in which is the original file messages. So zip by default preserves the directory hierarchy, and that's why it recreated it for us. Now that begs the question, can we avoid it altogether? Can we junk the paths? Certainly. That option is J. So let's remove rf var from our current directory, not the absolute var, of course. Let's echo the exit status. Let's ensure it doesn't exist, and it doesn't. So let's re-unzip, but this time we'll intersperse the J option. That junks the paths. Whatever paths, of course. And then this will create the original file. But of course, before we do that, let's take a look to see what we have insofar as the original file is concerned. Only compressed files, which is fine. So let's unzip with the J option, messages.zip. And now when we take a look at our current directory, we see messages, no original path restored, and then the compressed version. So you can junk the path if you'd like. And that's simply unzip with the J option, followed by one or more file names, unarchives the file sans path. So it simply terminates or junks whatever embedded file or path. So that's a little bit about zip, bzip2, as well as gzip.